Good morning, students. Today we shall learn about metals, non-metals, chapter 3, class 10 chemistry. So, we use a lot of metals and non-metals in our day-to-day life. Let's look at the samples of a metal and a non-metal. So, I have got sulfur powder in this test tube. You can look at it and observe it. The other sample I have in the other test tube is zinc metal. So when you look at it, what do you see? Both are solids. Both of these are solids, and sulfur is not very shiny, but zinc is a shiny object. So we draw this conclusion that metals are shiny, the solids, and non-metals are dull, mostly. Though there is a non-metal, diamond, which is very brilliant. Iodine is also a shiny non-metal. Let's look at other physical properties of metals and non-metals. So metals are solids except mercury. Mercury is a liquid metal, you all know. Metals are hard except lithium, potassium and sodium. I have a sample of sodium here, and this metal is not a very hard metal, so soft metal, it can be cut with a knife. So metals have a metallic luster that I had shown you, that zinc is shiny here. Metals are malleable, that they can be beaten into thin sheets, whereas non-metals are brittle. So when sulfur was ground, it turned into powder. You cannot turn the zinc piece into powder. Metals are ductile also, that the wires of metals can be drawn. They can be stretched without fracturing into wires. Metals have high melting and boiling points, whereas gallium and cesium can be molten in the hands. And mercury, as it is a liquid metal, so it exists at room temperature as a liquid. So a few metals have low melting points, but most metals have high melting points. Metals have high boiling points too, obviously. When they melt at a high temperature, obviously they boil at a very, very high temperature. Metals are good conductors of heat and hence are used in making cooking utensils. And metals are good conductors of electricity also, and that is why we use metallic wires as electric wires. There are a few metals which are excellent conductors. That means silver and copper are excellent conductors of heat as well as electricity, whereas lead and mercury are poor conductors of heat among metals. Let's look at the properties of non-metals, as we've looked at sulfur powder here, that non-metals, they are solids, but there are non-metals which are gases also, be it oxygen in the air, be it hydrogen, nitrogen, argon. So there are a lot of non-metals which are gases also, but many of them are solids too. So sulfur is one of the solid non-metal. Non-metals are not having a luster. They are soft and brittle mostly, but diamond is the hardest substance, you know. Non-metals are not malleable. They are not ductile even. Non-metals which are solids and liquids have low melting point. So there is a liquid non-metal also. Bromine is the liquid non-metal. Non-metals are poor conductors of heat and electricity both, whereas graphite, form of carbon, is an excellent conductor of electricity. That is an exception. Let's look at chemical properties of metals. What you observe here is, I'm going to show you a magnesium ribbon. Magnesium is a metal, and as we've learned that the metals are shiny, so it's supposed to be shiny. But with exposure to air, it has turned dull. Most of the metals you see in your surroundings, their surface turns dull because they are attacked by oxygen or moisture present in air. So metals react with air and hence they turn dull. This wasting away of the surface of metals due to exposure to moist air is known as corrosion. So this magnesium strip turns dull because of formation of oxides and carbonates on its surface. So when we use magnesium for any reaction, we rub it with the sandpaper to remove the outer dull coating. Let's look at how metals react with air. So when metals react with air, they form oxides, and the oxides of metals are basic in nature. That means if you burn this magnesium ribbon in air, it will produce magnesium oxide, and this magnesium oxide, when dissolved in water, will form magnesium hydroxide. And when that magnesium hydroxide is treated with red litmus paper, it turns the moistened litmus paper to blue. So that indicates that magnesium hydroxide is a base. So metals form metal oxides, and these metal oxides are basic in nature, whereas some metal oxides, they show acidic as well as basic property. For example, aluminium oxide is shown here, and zinc oxide also bears that kind of properties. So aluminium oxide, when treated with hydrochloric acid, it produces aluminium chloride and water. So what you look here is that it forms salt and water, whereas aluminium oxide, when treated with NaOH, which is a base, also forms salt, sodium aluminate and water. That means aluminium oxide shows basic properties in the first case when it is being treated with hydrochloric acid, and it shows acidic properties when it is treated with sodium hydroxide. So it shows amphoteric nature. Such oxides are termed as amphoteric oxides. Aluminium oxide and zinc oxide are two examples of amphoteric oxides. We can look at the reaction of zinc oxide with an acid and a base. Let's look at these reactions. So when we treat zinc oxide with an acid, we obtain zinc chloride and water. When we treat zinc oxide with a base, again we obtain sodium zincate and water. So what we look at, looking at these reactions, what we conclude is that zinc oxide, when reacts with an acid, acts as a base. So it is basic in nature here, and it forms salt and water. But when zinc oxide is treated with a base, again it forms salt and water, and we infer that here its nature is acidic. So zinc oxide also shows properties of an acid as well as that of a base, hence it is also an amphoteric oxide. The reactivity of metals with oxygen is different. So that means all metals do not react alike with the same vigor with air. So metals like sodium and potassium react vigorously with oxygen and catch fire when kept in open. You can again look at the sample of sodium. You find that sodium is put into a liquid, and this liquid is kerosene oil. So sodium and potassium both are stored under kerosene oil to prevent their reaction with air, because they can react vigorously with oxygen and catch fire, and that may lead to accidents even. If magnesium is heated, you've already looked at the magnesium ribbon. It turns dull due to reaction with the moist air, and when it is heated in air, I'm not performing this experiment that might lead to an accident. It's not a laboratory area. But when you burn magnesium ribbon over fire, it will catch fire to form magnesium oxide. So it needs to be heated. It does not react spontaneously. When iron is heated, it glows brightly, and you must have seen red hot iron sometimes. If copper is heated, it does not burn but forms a black coating of copper oxide on its surface. Silver and gold do not react with oxygen even at high temperatures, and some metals like magnesium, aluminium, zinc, lead, etc. form an oxide layer over it, and which prevents further oxidation. So magnesium ribbon, though it develops a dull coating, but this dull coating prevents further oxidation of magnesium metal. So such a case, it is called as self-protecting metals. Zinc is a self-protecting metal. Aluminium is a self-protecting metal. Reaction with water. So metals, how do they react with water? Again, I'll come to the sodium piece. Sodium is stored in kerosene to prevent its reaction with air as well as with the moisture. Sodium and potassium will react vigorously, rather violently with water, and they'll catch fire. Let me just show you the reaction of sodium with water. So here I have the sodium in the kerosene oil. With the help of the deflagrating spoon, I am putting it in the test tube. And with the help of so you see a vigorous reaction here, and the test tube ends up becoming warm, and you see the hydrogen gas evolving here. And if it was in a larger amount, it might have caught fire also, because hydrogen is an inflammable gas, and under high temperature it catches fire also. So to prevent the attack of sodium metal by air and moisture, we always store it in kerosene oil, and we reiterate that fact here. So we've seen that sodium metal reacts spontaneously with water, and that would be the case with potassium, because potassium is even more reactive than sodium, and it produces sodium hydroxide and hydrogen. Let's look at the equation again. So sodium reacts with water to produce sodium hydroxide and a gas which is produces hydrogen gas, and along with it heat is also produced. So if the hydrogen produces in larger quantity, along with heat, it might catch fire. So we balance the equation here. That is it. Calcium reacts less violently, but when calcium, like you've seen, the sodium piece also starts floating, calcium will also start floating, because the hydrogen which is produced is light and it will stick to the surface of calcium, and the calcium piece will start floating in water, though the reaction is less violent in comparison to sodium and potassium. Magnesium reacts only with hot water, it does not react with cold water. Metals like aluminium, iron, zinc react only with steam. In fact, iron reacts when it is red hot iron treated with steam. So you observe that the vigor of the reaction decreases. Sodium potassium reacts spontaneously, calcium reacts less violently, magnesium reacts with hot water, aluminium, iron, zinc react only with steam. Copper does not react with water at all. Copper, silver, gold, platinum, they will not react with water at all. They are known as noble metals. Reaction of metals with acids. So you can well imagine, if sodium which is treated with water to show a violent reaction, if it is treated with an acid, the reaction will be absolutely explosive. So sodium, potassium will react violently. Magnesium reacts vigorously. Let's look at the reaction of magnesium metal with hydrochloric acid. So we break apart a small piece of magnesium. I put it in this test tube, the magnesium rubber, and I'm pouring a small amount of hydrochloric acid carefully. What do you observe? Evolution of a gas. You see the fumes here, and the reaction is vigorous. When I touch this test tube, the test tube again gets heated up. So there is evolution of gas, magnesium. When treated with hydrochloric acid produces magnesium chloride salt and hydrogen gas is evolved and heat is also evolved in the process. Did we heat the test tube? We did not. So magnesium reacts spontaneously with cold hydrochloric acid. Aluminium metal is not here with us, but aluminium will not react as spontaneously as magnesium, not because aluminium is not a reactive metal, it's because as we learned that it is a self-protecting metal. It has an aluminium oxide layer around it and it will first dissolve the aluminium oxide layer in acid and then the reaction picks up and it is again a vigorous reaction. Zinc also will react in the similar manner. Iron will react a little less vigorously. Let's look at the reaction of iron metal with hydrochloric acid. So we have iron filings here. You see the iron, which is supposed to be a shiny metal, has turned dull again because of corrosion or rusting. So I'm pouring again hydrochloric acid very carefully into it. You see some bubbles evolving here, but is the reaction as vigorous as was in the case of magnesium? It indeed is not. So iron reacts less vigorously with hydrochloric acid in comparison to magnesium. We'll keep this test tube for some time and we'll touch it afterwards to find whether heat is evolved in this case or not. But certainly the hydrogen bubbles are evolving. So we can draw a conclusion that metals react with acids to produce salts and hydrogen gas. So we're keeping this test tube for some time to observe it later. What do you observe here? That the vigor of the reaction is again changing. Copper, silver, gold will not react with dilute HCl. Hydrogen gas is not evolved when metals react with nitric acid. So we generalize that when metals react with acids, they produce salt and hydrogen gas. But if they are they're treated with nitric acid, instead of hydrogen, we obtain water. Because nitric acid is an oxidizing acid, it will oxidize the hydrogen produced to water. So in case of any metal, say it's zinc metal reacting with nitric acid, instead of zinc nitrate and hydrogen will obtain zinc nitrate and water. Magnesium and manganese are two metals which produce hydrogen even with nitric acid. These are two exceptional cases. Now we are looking at the reaction of metals with the salt solutions, metal salt solutions. For example, if zinc metal is treated with copper sulfate solution, it will produce zinc sulfate and copper metal. Such reactions are known as displacement reactions. So if a more reactive metal is treated with the salt solution of a less reactive metal, it will displace that less reactive metal from its salt solution and it gets separated. So like there are three examples given here. Magnesium metal reacted with copper sulfate displaces copper. Zinc metal reacted with copper sulfate displaces copper metal. Again, iron reacted with copper sulfate displaces copper. Had we taken ferrous sulfate solution and treated zinc metal with it, that would also displace iron from ferrous sulfate. So there's a reactivity series of metals drawn based on the vigor of the reactions, based on the action of metals over air, water and acids. So potassium tops the reactivity series, being the most reactive metal. It is out of the common metals we are talking about. We are not talking about entire periodic table or all the metals. So potassium is the most reactive metal in the reactivity series, followed by sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, which is a non-metal. Why hydrogen is placed here? It is to find out whether certain metal will displace hydrogen from acid and water or not. So all the metals above hydrogen in the reactivity series are capable of displacing hydrogen from water and acids, and the metals below hydrogen in the reactivity series will not be capable of displacing hydrogen from water and acids. So here we have the reactivity series. There is a very common mnemonic to remember the reactivity series. So starting from K, Kejriwal. So I am just saying the mnemonic for your benefit. केजरीवाल ने कार मंगाई, ऑल्टो, जेन, फरारी, फिर भी हाय क्यों हार गई आम आदमी पार्टी. So that actually gives you the initials of or the symbols of all the metals in the reactivity series. Moving to the next slide. How do metals and non-metals react with each other? Here we had not talked about reaction of non-metals with water and acids because none of the non-metals react with water and non-metals do not generally react with acids also. It is only sulfur non-metal which will react with nitric acid. So mostly since the non-metals do not react with water and acids, we have not talked about those reactions. And non-metals on reaction with air or oxygen, they produce non-metallic oxides, and non-metallic oxides are acidic in nature. That fact you can bear in mind. Now we are moving to the reaction of metals and non-metals. So metals by nature, due to their electronic configuration, they have a probability or they have a tendency to lose electrons. Since they lose electrons and produce positive ions, they are known as electropositive elements. You can look at the examples of these two metals here. Sodium, which has atomic number 11 and electronic configuration 281, will attain the configuration of neon by losing one electron, and as a result it produces sodium ion, which is positively charged. Magnesium, however, has a configuration of 282 because its atomic number is 12, and it can lose 2 electrons easily to obtain the attain the configuration of neon. So here it will produce a magnesium double positive ion. These ions are positively charged ions known as cations, and these elements are known as electropositive elements. Non-metals, however, they gain electrons. Let's look at the configuration of chlorine. It has an atomic number of 17 units. So when it is 17, the configuration turns out to be 287, and by obtaining one electron, it can turn into the configuration, it can attain the configuration of argon 288. Hence, chlorine has a tendency to accept an electron to produce chloride ion. So this chloride ion is a negatively charged ion or anion, and non-metals are termed as electronegative elements. So let's look at the formation of sodium chloride, which is an ionic compound. Sodium, as we learnt, has a tendency to lose an electron, whereas chlorine has a tendency to gain an electron. So mutual transfer of electron, not mutual, it is the transfer of electrons from sodium to chlorine leads to formation of a sodium ion and a chloride ion. And these ions, since they are oppositely charged ions, they get bound by a very strong electrostatic force of attraction, and which is termed as ionic bond or electrovalent bond, and hence there is a formation of sodium chloride. Another interesting fact about sodium chloride is that it would not be in the molecular form like NaCl units. It always forms a crystal lattice. Crystal lattice I can show you here on the board. So here, suppose there is a sodium ion, there will be chloride ions surrounding it in all 6 planes. Then every chloride ion in turn is surrounded by sodium ions. Every sodium ion in turn will be surrounded by chloride ions, and due to this there will be formation of crystal lattice. So you cannot say that this sodium ion is bound with this chloride ion, this chloride ion is bound with this sodium ion. There is a crystal lattice, and that leads to formation of crystalline solids. We will look at the properties of ionic compounds. So this is formation of magnesium chloride. Here one magnesium atom can donate 2 electrons, whereas chlorine atom can take only 1. So the magnesium gives 2 electrons to 2 different chlorine atoms. As a result, there is formation of a double positive magnesium ion and single negative chloride ions. So there is 1 magnesium ion and 2 chloride ions, and hence there is a formation of magnesium chloride. The properties of ionic compounds. Ionic compounds, as I said, they are crystalline solids. They are formed by transfer of electrons. They have high melting and boiling points. Since they are solids and their bonds are very strong, they have high melting and boiling points. They are soluble in water but insoluble in organic solvents. They conduct electricity because they form ions. Hence they conduct electricity, but only in their molten state or in their solutions where the ions can move freely. Occurrence of metals. Metals, we've looked at metals that some of them are really very reactive and some of them are not. So the ones which are not reactive, they are found in free state like gold, silver, to some extent copper also. Whereas the reactive metals are found in the form of their compounds. And whatever form, whether they are found in the element form or the compound form, these are known as minerals. So minerals are naturally occurring inorganic substances. These could be elements, these could be compounds also. Those very minerals from which metals can be extracted are termed as ores, and when the ores are mined from the earth's crust, they generally have earthy impurities, and these impurities are termed as gangue. If a certain ore has high amount of gangue, it is termed as a low grade ore, and if a ore has low amount of gangue, it is termed as a high grade ore. So the steps in the extraction of metals. The extraction of metals from their ores is termed as metallurgy, and metallurgy is defined as the process of obtaining a metal from its ore profitably and conveniently. The first step that comes in the extraction of metal from its ore is concentration. So first the ore is ground or crushed to turn it into powder for the efficient separation of gangue from it. So the first step is concentration of ore, which is applied to convert a low grade ore into high grade ore. That means in this step the impurities are removed. There are different methods of removing the impurities. Then the further steps of metallurgy, they depend upon the reactivity of metal. Here, if a metal is of high reactivity, it just requires to be drawn from its molten ore through electrolysis. Whereas if the metal is of medium reactivity, it could either be a carbonate ore, sulfide ore or oxide. If it was an oxide, great, it would be processed further. But if it was a sulfide or a carbonate, it will be first converted into oxide. So if it was a carbonate ore, it is calcined. Process of calcination, that is heating the ore strongly in the air, in the absence of air is calcination, and heating the ore strongly in the presence or in the sufficient supply of air is known as roasting. So sulfide ores are roasted to convert into oxide, and carbonate ores are calcined to convert into oxides.